Hi, welcome you all to the 8th lecture of electroweak interactions in the standard model of particle physics. And today we are going to talk about the spin in Dirac equation. In last day's lecture, we introduced the Dirac equation, and today we are going to talk about some of its interpretation of the Dirac equation, and we are going to particularly talk about the spin of it. Okay, so let's get started. So, in quantum mechanics, we all know that the time dependence of an observable is given by this equation, like dO dt, which is also the expectation of that observable O with respect to time, and that will be I, the expectation of the commutator of the Hamiltonian with the observable and the expectation with respect to your wave function. Okay. So, this is how actually you can write the time dependence of an observable. Now, it is very clear that if an operator commutes with the Hamiltonian, like if H O is equal to 0, then it is very clear that dO dt will be 0, and therefore, that will be a constant of motion, and that can be called as a conserved quantity, right. So, let us first try to construct the angular momentum, which is simply, you all know that L is equal to r cross p. It is basically the angular momentum. The question is whether this angular momentum, which is defined as r cross p, is a conserved quantity in the case of Dirac equation for particles satisfying Dirac equation, for which what we need to check? We need to check the commutator of the Dirac Hamiltonian with the angular momentum, the commutation of the Dirac Hamiltonian with the angular momentum. Now, what is the Dirac Hamiltonian? Now, you all recall that we constructed this Dirac equation, which is alpha dot p plus beta m psi, which is equal to I del psi del t. So, therefore, the Dirac Hamiltonian, so to say, is alpha dot p plus beta m, and alpha and p beta, these are the 4 cross 4 matrices that we could actually construct, which was actually also constructed based on the fact that we have to retain the sanctity of this relativistic energy momentum relation, which is E square equal to P square plus M square, and we couldn't but to restrict the choices of alpha and beta to be matrices in 4 cross 4 dimension. Nothing else was possible. Two representations, one was this wild representation, the other which we are following here is what is called the Dirac-Pauli representation, right. So, this is the story so far. So, the Dirac Hamiltonian is alpha dot p plus beta m, okay, and the Dirac equation was essentially H d psi equal to E psi, which is E operator was I del del t, okay. So, let us try to construct the commutation of H d and L. So, what we have to do, that we have to compute the commutation of alpha dot p plus beta m with r cross p, and just this fact that beta m has nothing to do with r cross p. So, it is very well understood that they will commute. So, I am not bothered about that part anyway. So, the part which is interesting, or rather has to be computed, is essentially the commutator between alpha dot p with r cross p. So, let us do this computation. So, let us first take the Lx component, the x component of the angular momentum, and that is r cross p x component, and that will be essentially, as we all know, this will be y p z minus z p y, right, and these are all operators. On the other hand, alpha dot p is alpha x p x plus alpha y p y plus alpha z p z. Now, we all know that the main aspect of quantum mechanics was essentially the non-zero commutation relation between the position and the momentum, which basically tells you that x p x commutator is not equal to 0, rather I h cross in the natural units which we are following, we have chosen h cross equal to 1. So, therefore, we resort to these relations that x comma p x commutator, y comma p y commutator, z comma p z commutator, these are all I. Okay. Now, let us get back to this expression of H d comma L x, and here we see that okay, the interesting relations, because we have y and z here. So, and or rather and p z and p y here. So, it is important that we take this value, that alpha y, when you take you out, this will be p y comma y, because you have both the combinations like p y y minus y py, and pz will be on the other side, and minus of alpha z pz z commutator with py. So, following this above relation, these are simply minus y. So, therefore, this quantity turns out to be minus I alpha y pz minus alpha z py. Now, what is this quantity? This quantity is simply alpha cross p x component. Okay? So, it turns out that HD Lx is nothing but minus of I alpha cross p x component. So, therefore, we can also, without doing this calculation, but I suggest that you do this computation explicitly at home and check that HD comma Ly will be minus I of alpha cross p y component, and HD comma Lz commutator will be minus of I alpha cross p z component. Okay? Or in general, we can say that HD commuting with the orbital angular momentum or angular momentum, whatever that we want to say, it is simply minus I of alpha cross p. So, orbital angular momentum is essentially not a conserved quantity, because the commutator with the Dirac Hamiltonian is not equal to 0. So, the angular momentum is not a conserved quantity. The question is now that can we construct what we call the intrinsic angular momentum or the spin. So, you perhaps remember that when we learned in spin in quantum mechanics, the simplest representation was actually through, because spin was an intrinsic angular momentum which has same angular momentum algebra, but we couldn't resort to this explicit form of r cross p which we are using for the angular momentum, but our job was to find some matrices which actually satisfies the same angular momentum relations. Okay? So, however, here, because the spin operator has to work on the Dirac spinors, which are essentially 4 component spinors, right. So, therefore, we have to construct a matrix, intrinsic angular momentum matrix or the spin matrix, which is actually having 4 cross 4 dimension. So, therefore, what we are trying to do, that we are going to extend our 2 cross 2 spin angular momentum matrices to a 4 cross 4 one, and simple way to do that is to consider a spin operator which is half of capital sigma, or you can simply say this is half of sigma 0 0 sigma, a diagonal matrix involving the Pauli spin matrices, and this is once again going to satisfy the angular momentum algebra as like the orbital angular momentum case, like Sx will be Is and others you can also check. Now, let us check that what happens that if you take the commutation relation of alpha I. So, this alpha I are the the operators, or rather the matrices that appears in the Dirac equation with this x component of the spin operator that we have taken, which is sigma x. Okay? So, if you remember in our Dirac-Pauli representation, this is 0 sigma is 0, the alpha I, and sigma x is nothing but sigma x 0 0 sigma x. So, the commutation relation is simple, 0 sigma is 0 multiplied with sigma x 0 0 sigma x minus the other way around, sigma x 0 0 sigma x into 0 sigma I into sigma I 0. Now, this turns out to be simply a matrix which is 0, the commutator of sigma I sigma x sitting in the off diagonal position and 0, right. I mean, this is very evident from this algebra. Now, we also recall that sigma x commutator equal to 0, whereas sigma y sigma x is minus 2I sigma z, and sigma z sigma x is 2I sigma y. So, therefore, it is very evident that now if I take all these 3 different components of alpha i's, which are alpha x, alpha y and alpha z, then alpha x sigma x, this will involve the commutation with sigma x and sigma x, which is identically 0. Alpha y sigma x will be 0 minus 2I sigma z minus 2I sigma z 0, which is nothing but that if you take this minus 2I common, this is 0 sigma z 0, and that is nothing but alpha z. So, this is alpha y sigma x will become minus 2I alpha z, and alpha z sigma x is similarly 2I alpha y, right. So, now if I want to write the commutation between h d and sigma x, then once again I am not worried about the beta m part, because that will anyway commute and give you 0. So, the part which is interesting, or rather will give you a non-zero contribution, is only the alpha dot p part. So, this is alpha dot p commutator with sigma x, and which is alpha x p x plus alpha y p y plus alpha z p z comma sigma x, and alpha x sigma x is 0, alpha y sigma x is something that we found out minus 2I alpha z, and alpha z sigma x is going to give you 2I alpha y. So, therefore, I am going to write it, then this is minus 2I p y alpha z coming from this term, and this is 2I p z alpha y, which will be coming from this third term. So, together if you are going to write what is this quantity p y alpha z minus p z alpha y, this is nothing but alpha cross p x component of that. So, this is nothing but 2I alpha cross p x component. Similarly, now you can comment that if I take the commutator of h d with sigma y, then this should have been given 2I alpha cross p y component. If I have taken h d commutator with sigma z, this would have given 2I alpha cross p z component. So, together what we find is that h d comma s, this is half of h d comma sigma, and that is equal to I alpha cross p, right, because you have all these three components that are there for sigma x, sigma y and sigma z. So, therefore, S, the intrinsic angular momentum that we constructed, that also does not commute with the Dirac Hamiltonian. But now, let us see what happens that if we take the commutation of the h d with the total angular momentum, which is L plus S. So, h d comma j will be equal to h d comma L plus S, which will be equal to h d comma L plus h d comma S commutator. Now, tell me what we are going to get. h d comma L कितना हम लोगों ने निकाले थे? Let's go back. This is minus of I alpha cross p. Let's put that. This is minus I alpha cross p. And what is the h d comma s? This is plus I alpha cross p. तो मतलबन क्या हुआ कि एच डी एल का कम्यूटेटर जो रिलेशन है, जो क्वांटिटी निकाला है, एच डी एस से एग्जैक्टली ऑपोजिट निकाला है. सो दोनों ऐड करते हुए वी आर गोइंग टू गेट 0. सो देयरफॉर it is very interesting to observe that the j, the total angular momentum, which is L plus S, that actually commutes with Dirac Hamiltonian. So, therefore, you can argue that maybe this is a legitimate way, the S that we actually have constructed via this definition, that this is half of sigma, which is half of the Pauli spin matrices sitting diagonally in this 4 cross 4 matrices. This is a legitimate definition of intrinsic angular momentum or the spin of the particle satisfying Dirac equation, so that the j that we constructed, that is the total angular momentum, which remains a conserved quantity. So, once again, the rationale behind choosing the specific form of the intrinsic angular momentum sigma was following from the same algebra which orbital angular momentum actually follows, and that you should explicitly check. Okay? Now, the question that we would like to ask, that if we have borrowed this information and we have said that this S that we have constructed is really essentially can be identified as the intrinsic angular momentum or spin of the particle which satisfied Dirac equation, then the question can be raised that what is the total spin S that we can derive from here. Now, this is one relation that we all know from our quantum mechanics, that A square psi where psi is satisfying Dirac equation, say for example, will be giving you the eigenvalue s into s plus 1 of psi. So, this actually follows from L square L m, which gives you L into L plus 1 L m, where these are the eigenstates. This is what we studied in quantum mechanics. Now, what is a square? A square is 1 by 4 sigma x square plus sigma y square plus sigma z square, because the s operator is nothing but half of sigma, right. So, therefore, it is very easy to understand that this will be 1 by 4 of sigma x square plus sigma y square plus sigma z square. Now, let us compute sigma x square and sigma y square and sigma z square. If you do compute this, it turns out that this is nothing but simply the diagonal matrix 1 0 0 0 0 1 0 0 and so on. So, this is 4 cross 4 diagonal matrix, and there are 3 of this kind. So, this will lead to 3 by 4 into this thing. So, in a sense you can say that this a square is nothing but 3 by 4 into the identity matrix, okay? And this must be equal to s into s plus 1, right. So, s into s plus 1 equal to 3 by 4. What will be the possible s? This is a very simple algebra, and you can all check immediately that s is half. If you have s equal to half, then s plus 1 is 3 by 2 and s into s plus 1 is equal to 3 by 4. So, this is almost like a miracle that you interpret that the spin of those particle which actually satisfies Dirac equation is essentially spin half. So, the particles which satisfy Dirac equation has intrinsic spin half, or rather they are fermions, or in other ways we can also say that Dirac equation describes the spin half particles naturally in relativistic regime. So, therefore, the 2 degrees of freedom can be accounted for spin up and spin down states. So, we have already encountered the spin half objects before, and we know that when we take the projections, those spin can be spin up or spin down. Usually we denote spin up like this. So, this is spin up, and you have a projection which is spin down. So, these are the 2 possible projections that you actually have, or you can say that when Sz actually acts on them, they give you eigenvalues of plus half and minus half. But it is important that we should check explicitly if this is really the case for the solutions of the Dirac equation. So, let us do that, and in order to do so, what we need to do, that we have to solve the Dirac equation to some extent. Now, we all recall by now very well what is the covariant form of Dirac equation, that is simply I gamma mu del mu minus m psi is equal to 0. Now, the question is that if you have an object psi which is satisfying this kind of equation, what can be the possible solution of psi? Now, you say that this equation does not have any interaction, does not have any photon, does not have any electromagnetic interaction, blah blah blah. So, it is expected the solution will be plane wave solution, and how exactly the plane wave solution looks like? Psi xt will be something like e to the power I p dot x minus E t. This is something that we have already encountered, right. So, this is the part which will describe its energy momentum dependence, or rather position and time dependence. But we must preamble this with another part which is actually this u e comma p. Now, what is this u e comma p doing? Because e to the power I p dot x minus E t, this is a number or a complex number, so to say, right. The spinorial nature, that 4 different components which the psi inherits, because it has to solve the Dirac equation, and we have seen that it is a matrix equation and the solution must have 4 different components. those 4 different components are actually inherited in this spinorial part, which is UEP. So, that is the 4 component Dirac spinor part. Okay. Now, if this is your test solution, what we are going to do? We are going to bring it back to this main Dirac equation and see how exactly the solution looks like. So, the del mu psi, this part, because I gamma mu del mu psi, that is what you have to do, that is the operation, right. So, the del mu psi, the del mu part will act on what? The del mu part will act on basically this wave function part, I mean like e to the power I px minus et part. So, let us see, del 0 psi is del psi del t, wo kya hoga? Now, that will essentially act on e to the power I minus iet part, and that is going to give you minus ie, and that is going to give you. So, the del 0 psi will be simply del psi del t, and that is minus ie psi. What is del 1 psi? That is basically del psi del x. Now, you can tell me that it is easily obtained that this will be I px psi, because that is the component which is coming from this p det x part. What is del 2 psi? Del 2 psi is del psi del y, and that will be I py psi. What is del 3 psi? This will be simply I pz psi, right. So, now put all these ingredients back into the Dirac equation, which is I gamma mu del mu minus m psi. Now, so the del 0 psi have a preamble of gamma 0. So, it will be like I gamma 0 del 0 psi plus I gamma 1 del 1 psi, I gamma 2 del 2 psi, I gamma 3 del 3 psi minus m psi. Now, as we said that del 0 psi is nothing but minus I psi. So, this I square will become minus 1, and that minus will be absorbed, and this will simply give you gamma 0 e. What will happen for the second term? The second term, this I gamma 1 del 1 psi, because del 1 psi is I px psi, and with that I which is sitting here, that will also give you an additional negative sign, and this will simply becomes minus gamma 1 px, the next term becomes minus gamma 2 py, the next term becomes minus gamma 3 pz, and the last term is m, and this psi is essentially uep e to the power I px minus et anyway. So, now this equation is equal to 0, correct? So, this is equal to 0, this is the Dirac equation. I gamma mu del mu minus m psi is equal to 0, that is the Dirac equation. And now, because we have taken all the operations on the wave function part, and so I can completely ignore this part, and I can rewrite. And what is this gamma 0 e minus gamma 1 px minus gamma 2 py minus gamma 3 pz? You can simply say I can write it as simple as gamma mu p mu, where p mu has the 4 components like e, px, py and pz, and gamma mu has these 4 components gamma 0, gamma 1, gamma 2 and gamma 3. And we all know that when we take this product, there is a relative sign that is coming from the conversion between the contravariant to covariant via the g mu nu. So, therefore, this equation is turning out to be something which is very simple and very elegant, and it says that gamma mu p mu minus m acting on this spinor uep equal to 0 is the reduced form when we rewrite the solution of the Dirac equation in terms of uep into the e to the power I p dot x minus et, right. So, therefore, you can simply say that if I have to understand more of how this spinorial part of the Dirac equation look like, I basically now have to solve this equation, which is gamma mu p mu minus m uep is equal to 0. Let us try doing that, but today I am going to do it in a very simple manner, assuming that the particle is at rest. What does it mean? Particle is at rest. Every one of you already know that particle at rest basically means that this 3 momentum associated with this particle has to be equal to 0, right. So, this is p equal to 0. So, in that sense you can say that psi xt is reduced to u e comma 0 into e to the power minus I e t, as simple as that, right. Very good. Now, what I am going to do, that I am going to rewrite this above equation gamma mu p mu minus m u e p equal to 0 in the limit when the 3 momentum is equal to 0. Can you tell us what I should get? So, the gamma mu p mu minus m u e p, but the p is equal to 0. So, it will be only u e comma 0. What exactly it is going to be? Because the p vector is 0. So, this will be simply gamma 0 e, right, minus m u e comma 0 is equal to 0. That is it, because the p vector part is gone. So, this gives you a very simple equation. You know from Dirac-Pauli representation that we actually did, what is the form of gamma 0? What is gamma 0? The gamma 0 form is simply a diagonal matrix with the entries 1, 1, minus 1, minus 1. So, the equation that this equation looks like, that E into this gamma 0. So, this is your gamma 0, u e 0, this one I am writing as a 4 component spinor with these entries as phi 1, phi 2 and phi 3 and phi 4. So, these are the entries of the 4 component spinor. So, I am writing it like that. So, E into this quantity phi 1, phi 2, phi 3, phi 4 is equal to, I am bringing this term on the other side of the equation, is equal to m into phi 1, phi 2, phi 3 and phi 4, as simple as that. Now, it is very easy if you look carefully that what are the possible ways that I can choose the spinorial solutions. Now, one possible solution is when I choose u e 0 is equal to u 1 e 0, where I do not know what this normalization constant is for the time being and I do not care, but let me write the solution as 1 0 0 0. Okay? So, I am going to write it like this. Similarly, you can very well see that I can also choose this non-zero 1 at any of these positions of these spinorial places, right. So, u 2 0, u 2 e 0 rather, can be chosen as 0 1 0 0 with that unknown normalization constant, which I am not going to bother about. Now, if I choose these solutions, what will be the choice of E? What will be the solution for E? Can anybody tell me? Now, this is also very easy to see, because you see the gamma 0 matrix, this is 1 1, right, and if you put this 1 0 0 0, it is very easy to check that the E is going to be plus m for these two particular choice of u 1 and u 2. Now, I have two other possibilities. u 3 e 0 I can choose as 0 0 1 0, and I can also choose u 4 e 0 equal to 0 0 0 1, and just because I had these two negative signs over here, here and here in the gamma 0, can you tell me what will be the E values for these two cases? Yes, you are right. This is going to give you E is equal to minus m for these choices of u 3 and u 4, which is 0 0 1 0 and 0 0 0 1. So, therefore, there are 4 different possible spinorial solutions that we can have, and 2 of them are going to give me E is equal to plus m, that means positive energy solutions, and 2 of them are going to give me negative energy solutions, and those are essentially, you can say, antiparticle solutions, correct. So, therefore, psi 1, psi 2, psi 3 and psi 4 we can choose in 4 different ways, and this will be n 1 0 0 0 e to the power minus I m t, just because E is equal to plus m in these cases, and psi 2 is n 0 1 0 0 e to the power minus I m t, psi 3 n 0 0 1 0 into e to the power I m t, and psi 4 is 0 0 0 1 into e to the power I m t. Note in these cases that this is e to the power I m t, just because E is actually minus m. In this case also, E is equal to minus m. So, these are the two negative energy solutions and these are the two positive energy solutions. So, we are getting both particle and antiparticle solutions. Now, the question can be asked that I expected that it is good enough for me to have one positive energy solution and one negative energy solution, that is one particle like solution and one antiparticle like solution. But why do I have two particle like solution and two antiparticle like solution? Does that have something to do with the spin? The answer is yes. Let us construct the SZ matrix. So, you remember that we had the S defined, the intrinsic angular momentum which we defined was half of capital sigma, which was half of sigma 0 0 sigma, right. So, therefore, what is SZ? SZ is simply half of sigma 3 0 0 sigma 3. Very good. What was the choice of sigma 3? Sigma 3 was 1 0 0 minus 1. So, what is SZ acting on psi 1? Let us act explicitly SZ on psi 1. So, this SZ will be 1 0 0 minus 1, this is sigma 3. This is a 4 cross 4 matrix. So, I am explicitly writing the sigma 3 here to construct that 4 cross 4 matrix, and this is 1 minus 1 1 minus 1 in the diagonal entries, right. This is the SZ. What is psi 1? Psi 1 as per our solution, this is n 1 0 0 0 e to the power minus I m t. That is exactly what I write. Now, if you do this operation, what I am going to get? Can you guys tell me before I write? The answer is very, very simple. This is going to simply give me plus half psi 1, correct? What happens if I act SZ on psi 2? Psi 2 was 0 1 0 0 e to the power minus I m t. Remember, both psi 1 psi 2 were positive energy solutions, that means they are particle like solutions. But now, if I act SZ on psi 2, this is 1 minus 1 1 minus 1 acting on 0 1 0 0. Can you tell me what I am going to get? This is going to give me minus half psi 2. So, therefore, you see that these two positive energy solutions are basically aligned with spin up and spin down solutions. Psi 1 is going to give me the spin up solutions, whereas psi 2 is going to give me minus half as an eigenvalue of SZ operation, and this is going to give me spin down solution. Okay? And similarly, you can check and you must check that SZ when it acts on psi 3, this is going to give you half of psi 3 plus half psi 3, and SZ acting on psi 4, this is going to give you minus half of psi 4. That means there are spin up solutions for the antiparticles and spin down solutions for the antiparticles, because psi 3 and psi 4, these are the cases which gives you the negative energy solutions. So, the story comes here that these 4 different components that the Dirac solution, Dirac spinor actually inherits, they essentially imply to the particle like solution, antiparticle like solutions, and then there are 2 possible particle like solutions with spin up and spin down, and then there are 2 antiparticle like solutions with spin up and spin down, and these are all because that the solutions for the Dirac equations are essentially describing fermions, which are spin up objects which can have both the spin up and spin down representations. The story is not that simple. Remember, here we actually did a trick which is to look into the solutions of the Dirac equations when the particle is at rest, that is p equal to 0. The story is going to get slightly interesting and complicated when we try to find out a generic solution without p equal to 0, and for that we will have to go to the next lecture. Okay? So, today we are going to finish here and see you in the next lecture with more glorious technology and something which we call we have to define something called helicity. Just the spin is not going to work there, and we are going to derive the full solution of the Dirac equation, not for the particle at rest, but particle in motion. Okay? Stay tuned. Thank you so much.